Thanks for watching this video. This is going to be section 2.4, 2.5, actually 2.5 and 2.6. Section 2.5 and 2.6 from the book. Okay, let's get started. So, motion with constant acceleration. We talked a little bit about acceleration last time. But let's go ahead and get started. All right. So here we have a rocket, and when a rocket takes off, it requires a huge amount of force. And um, the typical, let's see, we can use the slope of the graph of the velocity to determine the acceleration of the rocket. So this is our rocket's velocity that changes as a function of time. Okay, and so if we take the slope of the velocity graph, that's going to give us our acceleration. Okay, and so we saw that a Corvette has an acceleration of about 9.5 meters per second squared, and so this rocket is 18 meters per second squared, so it's much higher. So there's a lot of force that goes into lifting a rocket, and yeah, according to the plot here, Vy, okay, we can find any 2 points here like it shows right here. So in 1.5 seconds, it increases by 27 meters per second, and that gives us 18 meters per second squared. Okay, erase that. Oh, no, it is there. That's in PowerPoint. Okay, we can use the acceleration Vx at some later time. Get rid of that. There we go. Okay, so we can use the acceleration to find Vx of f at some later time. Okay, so let's say maybe we know that what the initial velocity was, and we know its acceleration, then we can find the velocity later. Okay, and we've got our let's see, yeah, velocity versus time graph, and the area of this is the displacement. Okay, we saw that before. Um, and so down here, this equation is x of f equals xi. Okay, so you know what? Let's do an example here. Okay, let's use our the example of our rocket. And I don't know if you saw the latest mission that we sent some astronauts around the moon. This was really cool. The Artemis mission. Okay, 4 astronauts, and they went farther than from Earth than humans have ever been before. So really, really cool. Hopefully, we're going to go to Mars soon. Okay. And, people say, well, is it worth it? Is it worth the money it takes to go to outer space? I would say, heck yeah, because we don't know what we're going to discover along the way. Okay. So here's my rocket. Okay. And let's do an example. We know that our acceleration is 18 meters per second squared. Okay. And if you saw the Hail Mary project, this is really cool because actually, if you had a rocket that was accelerating at 9.8 meters per second squared, okay, let's say your guys were standing up here in the little space capsule on the top, okay, if you're accelerating at 9.8 meters per second squared, it's going to be like you're standing on Earth. Okay. These people would experience the same gravity that we experience here on Earth. For them, it would be no different. Okay. So that's something that's really cool. Yes. So these would be 9.8 meters per second squared. There would be it would be like there was gravity, which is why, Einstein realized that perhaps gravity is not actually a force. What is gravity? Well, it could be caused by the bending of space-time. And so if you're near something massive, like say the Earth or a star, the Earth bends space, and so you're falling into the Earth. And so that's why you experience this gravity, basically. Einstein described it like this: if our whole universe, okay, is like this stretchy membrane, okay? And we put something heavy like the earth, okay? Imagine now that this is like a trampoline. So I'm going to draw lines across here to kind of give you an idea what this would be like, okay? So if I had a stretchy rubber membrane, okay, then basically space and time are going to be bent like this, okay? And I say time because actually, when you do this, it doesn't just bend space, it also bends time as well. And so you get some really sort of interesting effects from the fact that, you know, heavy gravitational things are actually bending time as well too. Okay, so when you have this heavy object here, it's actually kind of like it's bending space around it. Okay. So the heavier the object, the more it actually is. And so if you're next to the earth or you're standing on top of the earth, you'll be here. And it's like you're always falling down into the earth. Okay. So these heavy things are actually bending space. So anything near here, like the moon, right? It can circle around here like a quarter on one of those things at the Science Museum. You put a quarter in and it swirls around. Okay. That's why we're attracted to the Earth because the Earth is bending space. All right, but let's go back to our example of a rocket ship here. Let's say that we want to know what is our velocity going to be after 100 seconds from liftoff. Okay, because it's going to take a pretty big velocity to escape the Earth. Okay, and let's say that our initial velocity is equal to 10 meters per second. Okay, 10 meters per second. And we want to know, well, at t equals, let's say, 120 seconds, so 2 minutes after launch, how fast is my spaceship going to be traveling? And I really do believe that I think that we're going to send people to Mars probably in your lifetime. I don't know when. NASA's planning on sending someone to Mars by 2035. Okay. And that's going to be pretty cool. So let's calculate our velocity here. So we have our final velocity equals our initial velocity plus AT. Okay. So if our initial velocity here is 10 meters per second. Okay. Then, okay, we're going to plug in our numbers here. So this will be 10 meters per second plus, then we're going to have 18 meters per second squared times t, which is, that's 120 seconds. Okay, that's going to equal our final velocity. Okay, so this will be 10 meters per second plus 18 times 120. Okay, so now I'm going to switch to MATLAB. And where did MATLAB go? I had it open. MATLAB, there it is. Okay, so here is my MATLAB, and I'm gonna make this bigger now because I can make this window as big as I want to. So I'm gonna copy in my numbers there. It's gonna be 10 plus 18 times 120 seconds. And so, wow. Okay, now that's pretty fast. Okay, so let's put this in miles per hour. Okay, so my velocity here is going to be 2,170 meters per second. And if I want to convert this into miles per hour, I'm going to go 2,170 meters per second times 2.2 miles per hour per 1 meter per second. Okay, so that's going to be roughly, it'll be about, let's say 4,000, and we'll say 4,700 miles per hour. Oh, might as well just throw in the calculation here. So let's say, uh, this whole thing here, and I'm going to convert it into miles per hour. So 2.2, yeah, 4,774 miles per hour. Wow. 4,774 miles per hour. And actually, probably let's go with what I had originally without the calculator. 470 miles per hour. Actually, it should be 480 miles per hour. Okay. So after 2 minutes at an acceleration of 18 meters per second, you're going to be going almost 5,000 miles per hour. Wow. Let's put that in terms of Mach speed. Mach is how many times you're traveling faster than the speed of sound, and the speed of sound is 343 meters per second. Okay, so we would have had to multiply that in there. Okay, so we'll multiply this times 2.2. Okay, so we'll get 343 times 2.2. Okay, so the speed of sound is 754 miles per hour. Okay, so we're going to take our results here. 4,774 divided by 754.6. Okay, so so in terms of our rocket speed, what this tells us is after 120 seconds, you're going Mach 6. Okay, that's fast. That is really fast. All right, we're cruising. All right, moving on. So our spaceship is really cruising here. Okay. Wow, that is incredible. Okay, so that's how we use this, and now, okay, we can say the shaded area can be subdivided into rectangle and a triangle. Adding this area gives the following. Okay, so let's say after 120 seconds, okay, and our initial speed is 10 meters per second. Okay, how many meters did we travel? Let's do that problem. Let's put this equation. So I'm going to write this equation here. So x final, okay, and x initial plus but actually, you know what? I don't know what that position is. So we're just going to say that this is off the launch pad. Okay? So off the launch pad, okay? We'll have our initial position there plus our initial velocity Vy, because this is blasting off, okay? I times delta t plus 1/2 ay times delta t squared. Okay, so um let's continue this example of the rocket. Okay, and now off of the launch pad, all right, off of the launch pad, let's say we want to know after maybe let's do 130 seconds to make up to for you to get to. No, actually, after 1 second, yeah, you'd be going 10 meters per second, right? Yeah, less than 1 second. Okay, that's fine. Let's do 120 seconds after launch. So xi initially is going to be 0. And let's say initially that our spaceship has 0 velocity because it's on the launch pad. Okay, that makes our problem a little easier. Okay, so how far did we travel? That's just this term's going to go to 0. This term's going to go to 0. Okay, so we just have 1 half a times delta t squared. And so after 120 seconds, okay, then we're going to have 1 half times 18 meters per second squared times 120 squared. Alrighty, let's put that into MATLAB. And there it is. Oh, and it even kept my camera settings. Wonderful. Okay, so we got that. I'm just going to plug that in 1 half times 18 times 120 squared. Wow. Okay. So that is going to give us then uh 129,600 meters. So that's 129,600 meters. Okay. Or let's convert it into kilometers. So to get into kilometers, that's 1,000 meters. So I'm going to move the decimal place 3 places over there. So that's going to be 129 kilometers. Wow, 129 kilometers. That is pretty high. Wow. Hey Siri, how high is outer space? Oh, Siri. Hey Siri, how high is outer space in kilometers?
I found this on the web.
Oh, Google, I want you to just tell me, Google. I mean, Siri. Outer space. How far does it start? What altitude? Okay. Oh, that doesn't seem right. So this is saying that outer space does not begin at a definite altitude above us, Earth's surface. The Kármán line, an altitude of 100 kilometers above sea level, is conventionally used to start of outer space in space treaties and aerospace record keeping. Certain portions of the upper stratosphere and the mesosphere are sometimes referred to as near space. Okay, so wow. That is you're pretty high up there after 100 and so after 2 minutes at that acceleration, you are getting close to outer space. Okay. All right, moving on. Now here, what do we got here in this velocity graph? Okay, the displacement x is the area under the graph. We talked about that last time. Oh, this equation of motion. Okay, so we mentioned last time, okay, the 5 kinematic equations, and somebody was asking me what equations should you put on your card? Well, that is one of the things that I want you to do as you're doing your homework, okay? So be thinking about what equations did I use to solve these problems? Which equations were most important? And that's what you should put on your card. But I would definitely have these kinematic equations on you. Okay, you're going to want to put these on your for sure. Okay, because you can use these for all types of a lot of problems. Okay, and so we talked about this equation. Yeah, we talked about this one. We talked about this one. We just did this one, and we did this one also. Okay, and now we're going to use this one. This equation is unique in the sense that it does not have time in there. So after you do um after you do a bunch of algebra that I'm not going to go through in the video because there's a lot. You can get to this equation, and you can get this equation from the other equations, but for our purposes, we are just going to accept that they derived this. Okay, takes a couple pages of algebra to get to this one, but it comes from these other equations. You can substitute these equations into each other, and you can get this one. And this is useful because there's no time. No time. Okay. So sometimes if you know the velocity, right? Maybe you want to know how far it traveled and you know the acceleration. You don't need time in here. So this one is kind of a shortcut because a lot of times in these problems, it's a great strategy to solve for your time. In fact, whenever I have problems like this in this chapter, this is my kind of three is my go-to equation. I'm always like, equation number three, right? It's the all-purpose equation that you can use for everything. And oh, we got EV's velocity here. I'm just gonna remove this, okay, so we can focus on the equation here. Yeah. Okay, so when you make your card, maybe don't make mistakes. Okay, so x of f, our final position equals our initial position times our initial velocity plus 1/2 at squared. Okay, and I should probably rewrite that, but you know which one I'm talking about. So put these on your card. All right, so let's do an example with this one. Okay. For motion with a constant acceleration, okay, I'm gonna shrink this down here. We'll put my card over here. Probably want to write a little smaller than there. Okay. For motion with a constant acceleration, velocity changes steady. The position changes as the square of the time interval. We can also express the change of velocity in terms of distance, not time. Yes, that is all true. And oh, you can also do ratio, right? We did a ratio in a couple videos ago. So, for example, if I know my position at two different times, okay, then and they have the same velocity, right? So let's look at, say, this equation up at the top. Okay, let's go here. So if I know my, oh, I'll make this. There we go. Okay, so over here, I'm going to do an example. I'm going to say xi initial is equal to my velocity times t initial, okay? And I can divide this by x final minus v times t final. Okay, so that's nice because my velocities cancel out, and now I just have this fraction here. Okay, so xi over x of f equals ti over tf. Okay, and now I can solve for my final time or my final position. I don't care about the velocity. Maybe you don't know the velocity. Okay, you don't need it. You can just use this ratio. Okay, ratios can be handy sometimes for certain problems. So maybe you don't know what the velocity is. Okay, and you're like, I don't have enough information for this problem, but you have two positions and you have one time, you can find the final time or you can find the final position. Right? If you have one unknown, then you just need one equation to find it. And remember, each equation is really just a little miniature experiment. Ah, words to live by. Okay. Yes. So you can use scaling quadratic relationships. Okay. Ratio of y2 to y1 is the square of the ratio of x2 to x1. All right. Yeah, we can go through this. All right. Example, coming to a stop in a car. All right, where are we at here? How many slides do we have? Oh, don't go over there. All right. What slides are we at here? Okay, what are we doing? All right, we're almost to the end of this section. I know that sometimes these videos get a little long, but I want to explain it. And I don't know if you necessarily need this. One student was saying that they're reading the book and taking notes on the book. And if that's what works best for you, then you should do that. Okay. But I'm making these videos here in case you have questions, and there will be lots of example problems. So if you don't understand something, check out the videos, but you can also just read the book and take notes. Either way, it's fine. The videos are not required. Hopefully, they're helpful and maybe funny. Hey, wow. Thank you, Bulbasaur.